Okay, welcome to the ACA Manual D Residential Duct System Design. This is part 2, choosing a blower. This is again part of the HVAC Essentials program that ACA makes available, and I am your presenter, Jack Rise. If you haven't been through part 1, please go back and start at part 1, because we're going to use a lot of the information from part 1 in this part and the next parts that follow. So again, this is a progressive series. I will warn you about that. Again, our purpose is to give you a system that is designed properly from an efficiency, from an effective and from a noise standpoint. We would ask you very seriously to consider Manual J, Manual T, Manual S. You should have these under your belt at some point in time before you apply any of this information. And again, this is progressive, part 1 before part 2, so on and so forth. And any use of the information in here is totally at your own risk. Again, our concern would be that you didn't understand what was said, or you might misapply something if you really don't get the understanding involved here. We're going to talk about a lot today, and the most important thing, the thing that I would like to think I spent my adult life defeating, is this myth of 0.1 static pressure, that you can go to a duct calculator, pick it up, and just put whatever volume of air you want opposite 0.1, and that automatically gives you the duct size. I wish life were that easy. It's not. Nothing is. My dad used to say, if you make a system so easy that even a fool could use it, then only a fool would use it. Trust me, this applies here. We're going to talk about the ACA wedge, because I think that was one of the sources of the misunderstanding we have with 0.1. Air duct calculators in general. I'm sure I'm going to tell you something today about air duct calculators you probably don't know. Friction rate formula. Available static pressure is involved with the friction rate formula. Total equivalent length. You'll have an explanation for all these terms. Simple system example. We're going to give you an example of a system that's already done and show you how it was developed. Choosing a blower, which is what we're getting to today, the highlight of today. Blower performance chart. Furnace blowers versus air handlers. There's a difference. Okay, if you know how to read both charts, it's no sweat. All right. Compare that to using 0.1 inch static pressure. Okay. So if you're ready, I am. Let's hit the start button and get going here. All right. First of all, let's talk about this 0.1 deal. If I were to come to you and say, what size duct would you choose for 1200 CFM of air? You'd whoop out your trusty duct calculator, and you would show me up top here where it says 0.1 should be used. It says right on a duct calculator, recommended residential setting. Okay? And as true as that is, that's easy to misunderstand. Okay? There's a couple issues you have to be aware of. First of all, this duct calculator that you picked up is only good for plain round metal. Okay? Any duct calculator you pick up that's not stated otherwise is for plain round metal. Let me go over each of those one at a time. Plain, not line duct, not fiberglass duct board, not rigid round. Plain round. Round, not rectangular, not oval. A 6-inch oval pipe gives you less air for the same pressure as 6-inch round. 5-inch oval, less air than 5-inch round. All right? Not rectangular duct, not square duct. Round duct. Metal duct. All right? Not flexible duct. Certainly not flexible duct. All right? Not rigid round, not any other kind of duct. Not PCD duct, not any other kind of duct. All right? Plain round metal. All right? Again, if I were to pose the question, and you would be doing only what I did years ago until I learned better, is that you would put 1200 CFM of air opposite 0.1 inch static, and you would tell me that you need a, what is it going to be, about a 14.5 inch round duct would be perfect. And you know, that may or may not work, but I can almost guarantee you it won't work. And I'm going to explain why. And let me just avert here for a minute. What size flex duct would you use? I just told you can't use this for flexible duct. Well, I took a flexible duct calculator and I laid out three values, 0.06, 0.12, and 0.18. So if you wanted 1200 CFM, you would have to be not a 14.5 inch round. Let's find 1200 CFM down here. You would have to be at an extremely high static pressure, or with 16 inch, or 18 inch would be just about the size you need. Now I know you're going to tell me I'm nuts for using 18 inch on 1200 cubic feet of air, but I can, hopefully by the end of this program you will understand the importance of that. And the reason is, let's say you wanted 100 CFM, 120 CFM. What size duct are you going to use? 6 inch round would probably do fine, but look at this, 120 CFM. You're all the way off the right side of the chart here that I'm going to explain to you in a minute at 0.18. That's very high static pressure. That's noise. All right. If you want the same, that CFM, that 120 CFM, you're going to be in this area. You're going to be in a 7 inch duct. Rule of thumb, if you do nothing else, rule of thumb, and I hate rules of thumb, but rule of thumb, go one size up when you're choosing a flex duct. It doesn't always work. It might, your velocity might go in the can, and it might be a real problem for you. But at least do that part right. Okay? Now, what's the problem with flexible duct? That's the problem with flexible duct. This irregular surface, this corrugation, is the problem with flexible duct. And the more tightly compressed that flexible duct is, the worse it is. All right? Flexible duct should be installed fully extended. That means you pull it out as tightly as you can, which means that all your fittings that take off to the trunk duct, the ceiling box, the whatever you're connecting it to, has to be nailed down, if you will, correctly. All right? You can't just come off the top of an 8x8 to 8 inch ceiling box. You know, you have to put an elbow in there if it's a top outlet box, and that elbow has to be screwed to the top of the box, and you know, then the flex is cut and pulled tight and secured to the elbow, and the other end is secured to the side takeoff or whatever you have on your trunk line. All right, that's the way it's supposed, because the further away you get these corrugations, all right, the less turbulence you're going to have in airflow. All right? And the less turbulence, the less resistance, and you know, from the part one, the less resistance you have, the more airflow you're going to have. This is what I think has a lot to do with, maybe not this directly, but this concept of how a duct system should be designed. If you read ACA Manual D, or if you ask an ASHRAE engineer, how should a residential, what friction rate should a, and we're going to talk about that in a minute, should a residential duct system be designed at? He will say somewhere between 0.06 and 0.18 inches of water column per 100 feet of duct, because it's a rate. All right. Now, what's right in the middle of all that? This is what they call the ACA wedge. Okay, if you stay within this wedge, you'll have a good residential system. Again, right in the center, 0.1. Actually, mathematically 0.12, but we all like round numbers. All right. I got a feeling a long time ago somebody asked somebody, and somebody made some generalizations, and I know there were 2 or 3 salesmen involved. I can be sure of that, and kidding the salesman, but this may well be where that came from, because if you give people a choice and you say, well, this is the minimum and this is the maximum, where do you want to be? Well, you want to be dead center between the worst and the most. That's a natural inclination. And that's true. That's where we want to be, at 0.1 or somewhere around 0.1, anywhere between 0.6 and 1.8. But we can't start there. We can't just assign a static pressure to a piece of duct. We have to calculate to get there. Okay? Now, I started talking about friction rate. Friction rate is a rate per 100 feet of duct. Okay? All duct calculators are based on that, 100 feet of duct. If you have 200 feet of duct or equivalent feet of duct, that friction rate changes. Okay? This is per 100 feet. Static pressure is a term that applies to reading a pressure. It's like me saying, well, I went up to the water system in the house and I hooked up my water gauge and I read 50 pounds of city pressure. Okay, that's fine. What's the flow rate? How many gallons per minute are flowing through that pipe? I have no idea. Well, what happens to the pressure when the flow starts? I have no idea. All I found was that, well, you're saying the same thing when you say static pressure. All you're saying is, well, I have a static pressure. It's X. It's 0.5 inches. Okay, well, that doesn't say anything about the system whatsoever. Friction rate is a rate per 100 feet of duct, and you got to understand that. This is not 0.1 static pressure. This is 0.1 inch as long as there is 100 feet of equivalent duct, or every 100 feet of equivalent duct has a 0.1 inch drop, is another way of looking at it. Okay? The friction rate we're going to enter a duct calculator with is equal to the available static pressure times 100, because it's per 100 feet of duct, divided by the total equivalent length. What's available static pressure? Available static pressure is the pressure remaining that can be used to design a duct system after all external components have been deducted. Okay, after. Example, a furnace has a blower that will deliver 1200 CFM against 0.7 inches of water column external static pressure. You've seen that on the blower performance chart. Okay, so our blower can overcome 0.7 inches of water and still deliver 1200 CFM. Now, the evaporator coil, wet, has a 3.0 drop in this particular case. We have to subtract that from the 7.0. We're only left with 0.4. Okay? Well, you got other systems in there. You have an air cleaner that's imposing an external pressure. That's 0.2. Now our blower's down with only 0.2 left over to design a duct system. 03, 03, 03, registers, grills, volume dampers. That total is 0.09. The result is our available static pressure with this particular blower is down to 0.11 inches to be exact. Okay? Now we have to, you say, oh, that's great, I got 0.1, that's what I need for a duct system. Not so fast. That's not enough. That's not nearly enough. Let's finish this equation. We're trying to solve for friction rate. We know what the available static is. It's always times 100 because we're using a duct calculator. And the TEL now is what we have to determine. TEL is the total effective or total equivalent length, is the sum of the longest measured length, measure it with a ruler, of trunk and branch duct plus the equivalent length of all the fittings in that run. Okay? Okay, in the back of Manual D, starting in Appendix A, in fact this is page A3-3, you will see equivalent lengths for fittings. For instance, let's just jump right into this. Take this connection here where we have a round piece of duct coming off of a supply plenum. Okay? Now, that's this is the isometric view, of course, for this. Now, this is a typical flat A collar we all know and love. And I don't recommend taking branch lines off of plenums, but this will serve the purpose. What you will see here, they're going to call this a 1-A fitting. That doesn't matter. What matters is the EL, the equivalent or effective length, is 35 feet. That means turning air out of this plenum into this collar is equivalent to 35 feet of straight duct. The pressure drop is equivalent to 35 feet of straight duct. Pretty easy thing to measure. You measure the pressure drop through there with accurate instruments, then you set up a blower with straight duct on it, and you go out away from the blower until you hit a point where you have the same pressure drop, and you say, oh, look at this, I'm 35 feet away from the blower. Very simple thing to do, fairly accurate. All right. Can we improve this? Yeah, we can. There's a way to do that by creating wide mouth branches. This fitting, all right, same situation, except it's not round, it's a duct, or it's at least a rectangular duct. That's the side view of it. The fitting is the same, has the same equivalent length, 35 feet. Pushing air from here to here has the same pressure drop, is the same lack of air or the same loss in airflow as pushing air 35 feet down a straight piece of duct. That's what these EL means, and they all mean the same thing. Can you improve that from 35? Yeah, you can knock it down